It's for me a pleasure to introduce all of you Jaime Pignatelli. Jaime is a degree in biochemistry from the University Rovira y Virgili in Tarragona in 2002. Then he moved to Madrid to perform his PhD at the National Centre of Biotechnology at the CSIC, and obtained the PhD degree in molecular biology in 2007 from the Universidad Autónoma de Madrid. He then moved to work at the Cajal Institute from 2010 to 2013, and later to the INEA from 2013 to 2017. And finally, he went back to the Cajal Institute to work in the group of Ignacio Torres to carry out a project focused on the role of IGF-1 and mood. In 2021, he got a position as a doctoral researcher at the Cajal Institute, where he continues his studies on the role of IGF-1 in the brain related to neuroplasticity, mood, beta-amyloid metabolism, and neurodegeneration. He's also responsible for a new unit of next-generation sequencing at the Cajal Institute, and his webinar today is entitled Insulin-Like Growth Factor I Couples Metabolism with Circadian Activity through Hypothalamic Orexin Neurons. So Jaime, thank you very much for your willingness to share with us your work today, and welcome to this webinar series. Please just go ahead. You can share your screen and start.
Okay, thank you, Miguel, for your kind introduction. Can you see my presentation?
Yes, you have to put it on full screen.
No.
Yes, perfect.
Okay, thank you. Thank you everyone to assist this webinar this afternoon. Today I would like to talk about insulin-like growth factor I couples the metabolism with circadian activity through the hypothalamic orexin neurons. This work has been recently published in International Journal of Molecular Science. If someone is interested, just follow this QR code with your cell phone or whatever. This work was performed in the Cajal Institute, but with Ignacio Torres Alemán from Achucarro Bas Center for Neuroscience. First of all, let me give you a brief introduction about the biological rhythms and the wall homeostasis. Every single cell from our organism possess their own circadian clock machinery. That is a set of genes, beta-mal, clock, parenchyma, that constitutes an oscillator. Okay, it's a transcription, translation, feedback, inhibitory loop. Beta-mal and clock drive the expression of per and cry, and these two genes, per and cry, at the same time are able to inhibit the beta-mal and clock expression. So that's how they achieve an oscillation on their own expressions. On the other side, beta-mal and clock also drive the expression of another genes that are named clock controller genes. But following this oscillation of expression of beta-mal, they have rhythmic expressions over the day. Okay, these transcription factors that are ROR, PAR, REP-F, SREP, GBP, TEF, and 8LF drive the second set of clock controller genes that follow the same rhythmic expression over the day. Okay. Using this strategy, animals express those genes depending on the daytime. Okay, for example, in diurnal animals as primates, beta-mal and cry are expressed at the beginning of the inactive phase of these animals, whereas the cry and per one are expressed at the beginning of the active phase. In the case of nocturnal animals like mouse, it's the opposite. Beta-mal and cry are expressed at the beginning of the inactive phase. It means at the beginning of the diurnal phase, and per and cry at the beginning of the activity state. In that case, in the dark phase. Okay, so you can understand that if every single cell from our body have their own clocks, if we change our vision to the whole organism, they will be thousands and millions of different clocks moving in different ways. So that would be difficult to the body to feed all the functions of the biological functions working together. So there are is a signal. That signal is the circadian entrainment, okay, to synchronize all these clocks. In that case, for the circadian entrainment, the most important signal is the sunlight, or the light in the case of mice in the stabulary. This sunlight is received by the prechiasmatic nucleus, okay, and information is integrated in the secondary hypothalamic regions, and this information is sent to the rest of the body through the HPA axis and the glucocorticoid release. Okay. There's a second entrainment signal, that is the metabolic entrainment, is based on the nutrients levels into the blood. So, and this, in addition to this nutrients availability, peripheral organs also send information about the metabolic status of the body with neuropeptides like renin, leptin, adiponectin. This information, these nutrient levels and neuropeptides are received in the hypothalamus, in the coatus nucleus, and also medial hypothalamus and the lateral hypothalamus. It integrates all this information and sends a signal to the rest of the organs through the autonomous peripheral nervous system. Okay, so at the end, what we have is a mixed signal coming from the sunlight and also from the metabolic entrainment. Okay. Another secondary entrainers could be the feeding time and also the exercise. So that's a resume of all this information. So since every single organ have their own circadian clock, they have their own rhythms of expression of the functions. So it's required synchronization of all these rhythms to achieve a single rhythm to maintain the biological functions properly fitting with the animal lifestyle. Okay. So, but there are some disruptions of this resonance, of this synchronization, that can affect the amplitude of these rhythms or the phase, the time where they change. Okay, and these disruptions are risk factors for different pathologies. For example, in the central nervous system, we have sleep disorders or mood disorders and neurodegenerative diseases. In the case of metabolic, we have obesity or diabetes. In the case of immune system, we have autoimmune disorders. So the main circadian disruptors are the aging, natural aging, but also other ones related to the lifestyle, like fat diet, shift work, or the stress. Okay, that graph I want to show you how these circadian disruptions can affect the individuals at different age stages and causing different pathologies with different severities. We can observe here in babies irritability and mood swing, in teenagers fragmented sleeps, anxiety, and in adults and older adults we have rheumatoid arthritis, osteoarthritis, and more severe pathologies like Alzheimer, Huntington, type 2 diabetes. Okay. So the insulin-like growth factor I is a multifaceted peptide related to insulin. There's a broad literature about this growth factor. The main functions are the glucose metabolism, the neural development, mood, and also vitamin amyloid clearance. Okay, the expression of the IGF-1 it is produced in all cells from our body, but mainly in the liver. Okay, and it's regulated by the growth hormone and somatostatin axis. So regarding circadian rhythm, there is less literature, but it has been shown or published that the IGF-1 injection is able to synchronize the pair clock gene into the liver. Okay. The second actor of this work is the orexin neuropeptide, and it's also a multifaceted neuropeptide that is related to the sleep, metabolism, and mood. Okay. This neuropeptide is synthesized by a very small population of neurons that are located into the hypothalamus, the lateral hypothalamus. There are few neurons, but they are broad innervating the very different regions from the brain. So, and they participate in a lot of circuits relating aspects as sleep, metabolism, mood. Okay. Regarding the circadian rhythm, it's known that they participate in circuits that are regulating the light entrainment and the food entrainment. Okay, so with other brain regions are driving the daily rhythm in physiology and in behavior. Okay, we wanted to know if those IGF-1 could be regulating the circadian rhythm through orexin neurons. To do that, we use a mice strain that we have generated in our laboratory that is called FIROG. These animal mice have a clear combinase expression under the promoter of orexin, and we have the gene of the IGF-1 receptor fluxed into the exon 3. Okay, so in these mice, the IGF-1 receptor is mutated specifically in orexin neurons. Okay. We first demonstrated that these neurons are insensitive to the presence of IGF-1 by an intraperitoneal injection of IGF-1. We perform immunohistochemistry to detect the CFOS expression in this mice. We observed that in control mice, the injection of IGF-1 induced an activation of these neurons, whereas in the FIROG mice there is not activation. Okay, so regarding the circadian rhythm, we know that orexin expression is regulated by follows a circadian rhythm. Okay, and it's with a peak of expression at the beginning of the active phase. In that case, at the beginning of the dark phase for a nocturnal animal. Okay, we analyzed the levels of transcription of orexin at different time points, and we observed that at CIBERNED in control mice we have a peak of expression of orexins, but not in FIROG mice, where it seems to be delayed. Okay. So if circadian expression of orexin is affected, we wanted if there could be affecting the different the behavior, the normal behavior of those mice. So we use metabolic cages to analyze the feeding pattern, the activity behavior, and we performed this experiment in males and females, FIROG mice and control mice. As you can observe here, in case of males, we observe that they have an advance of the feeding time, okay, that produce an advance of the feeding circadian phase about 1 hour and a half. Okay, we didn't see any difference regarding the activity behavior, and in females, we didn't observe this feeding alteration, and neither in activity. Okay. In the previous experiment, since there are normal conditions of light and food, the circadian entrainment prevails over the other ones. So we wanted to analyze if maybe only the metabolic entrainment was affected in those mice. So to do that, what we do is we uncouple the circadian entrainment just by switching off the light in the cages, and we move the food time to the period, the inverted period. Okay, so in that case, we move the feeding time to the period where it should be light. Okay, using this paradigm, we observe that different days animals are used to this new feeding time. When we move the food to the contrary, to the opposite phase, they learn to feed at this time, and they have the same. They eat the same amount of food. However, the control mice follow the normal or the regular dusk to dawn phenotype. That means that they have the same. They take most of the food at the beginning of the period, the feeding period, and small snacks at the end of the period. Okay, in the FIROG mice, they don't distinguish or not. They show this feeding pattern affected. Okay. So To go in deep about if metabolic entrainment could be affected, we try a new paradigm. In that case, we potentiated the metabolic entrainment versus the circadian or other entrainment signals using a feeding restricted time. Okay, so we use the same conditions about light in the previous experiment, but we move the feeding time only for 6 hours during the inactive phase. And we also add a running wheel in the case, because when we use this paradigm, animals learn when are you going to provide the food, and they anticipate it, and they start to run. So, and you can measure the activity as a readout for this metabolic entrainment. Okay, that's what is known, the food anticipatory activity. That is a curious phenomenon that is not exactly described, and we are not sure about what are the neurons that are implicated on this behavior. It's known that, for example, in orexin knockout mice, this activity is decreased, and in lesions in the dorsomedial hypothalamus, this behavior disappears. Okay, but in our case, what we obtained after the 5 days of conditioning is that few of mice have an increased food anticipatory activity with regard to the control mice. So that means that the metabolic entrainment in those mice is more potentiated than in control mice. So we have a misalignment between the circadian and the metabolic entrainment. Okay. To confirm that those mice suffer a circadian and metabolic misalignment, another good readout is the circadian glucose rhythm. Okay, the circadian glucose rhythm depends on the information coming from the suprachiasmatic nucleus. Okay, and this information is sent to the paraventricular nucleus and to the peripheral area, where the orexins and also the neurons from the paraventricular nucleus provide a signal to the liver to promote the glucose peak at the beginning of the active phase. So what we do is analyze the glucose levels at different time points in feed and control mice. And what we observe is that whereas in control mice we observe a clear peak of glucose at the sedative 14, and also in females. In feed mice, males, we observe that this peak is broadened and is advanced for several hours than in control mice. We did observe this phenomenon in females. That means that we have a sexual dimorphism regarding the glucose circadian rhythm in feed mice. We wonder these results could be affecting the insulin circadian rhythm. We tested it in males and in females, and we didn't observe any difference, although they show higher levels in both males and females. That we interpreted these results as they are developing hyperinsulinemia. Okay, if we wanted to go deep about the sexual dimorphisms on the glucose response after orexin function, what we did is in one-time mice, we injected orexins intracerebroventricularly at the beginning of the inactive phase, where orexins should be downregulated, and we measured the glucose levels at different time points after the orexin administrations. As you can see here, both males and females showed an increase on the glucose levels after the orexin administrations, but this effect was higher in males than in females. So if the feed mice have a misalignment between the circadian and metabolic entrainment, as I told you at the beginning in the introduction, it's a risk factor for the development of metabolic alteration. So we analyzed different metabolic patterns, parameters, and we observed that in males, they develop with age. In adult male mice, feed mice show fasting hyperglycemia. That's a marker for diabetes, and they also develop glucose intolerance with age. Okay. In the case of females, we observe that only in adult females, we observe obesity, and this obesity was due to the accumulation of fat tissue in the viscera and ependymal regions. So we wanted to know if how IGF-1 could be regulating the orexins to develop this phenotype. So what we do is we injected IGF-1 ECV in mice, in male mice, at 2 hours before the beginning of the active phase, and we determined the levels of orexins 2 hours later. So as you can see here, in control mice, the administration of IGF-1 don't regulate the expression of orexins, and that didn't happen in field of mice. So as I told you before, beta-mal and PERS and CRY are the central oscillatory clock. There are other secondary clocks like DBP, TF, HLF, and there is another family that is known the Krapel-like family. And one of these factors, the CALF10, follows a circadian rhythm, obviously, and it's also related to the glucose metabolism. Okay, so in knockout mice of CALF10, males develop hyperglycemia and glucose intolerance, and females develop obesity. So we wondered if this IGF-1 and orexins could be regulating the transcription factor of the expression of this transcription factor. So we performed real-time PCR in liver from the same mice in the experiment. What we observed is that in control mice, administration of IGF-1 induce and regulate the expression of this transcription factor, whereas not in field of mice. On the opposite, if in field of mice, CALF15 was upregulated, but not in control mice. That's interesting because all these three members of the same family, they are sensors for the nutrients availability, but one of them, each of them, depending on the different nutrients. In the case of CALF10, it's more related to carbohydrates, and in the case of CALF15, it's more related to amino acid metabolism. So, whoa. Oh, sorry. So, as conclusions, IGF-1 signaling in orexin neurons balance the metabolism and the circadian entrainment. IGF-1 signaling in orexin neurons regulates the glucose circadian rhythm. IGF-1 signaling in orexin neurons is relevant factor to maintain the metabolic homeostasis in a sex-dependent manner. And IGF-1 levels declining with age during a natural process that is known as somatopause could be a relevant factor for the development of metabolic pathologies and consequently a risk factor for severe pathologies, including neurodegenerative diseases. So, as I told you at the beginning, one of an important effect or pathology developed with the misalignment between circadian and metabolism or alteration of the circadian rhythm is the development of neurodegenerative diseases. So we wondered if this field of mice could be developing any affectation of, and we performed a very small trial using 18-month-old field of mice, females, and we performed an analysis for the A-beta 40 in hippocampus of those mice, and we observed that in field of mice have significant higher levels of this peptide in the hippocampus, suggesting that in field of mice we have an increased amyloidosis. So there could be a second effect of the circadian and metabolic misalignment. We didn't observe any change on cognition, but we observed that the decrease on orexin levels is a natural process. We detected that comparing not control mice with 3 months old and 18-month-old, there is a decrease, a natural decrease on orexins. Okay. So thanks to all the people from my laboratory, especially to Maria Estrella Fernandez de Sevilla and Jacob Sperber, Also thanks to Ignacio Torres Alemán and people from his lab, Patricia Miranda and Jonathan Segarra from the Achucarro Bar Center for Neuroscience, and also to Gemma Medina and Daniel Orrillo from the Universidad Rey Juan Carlos. Thank you.
All right, thank you very much, Jaime. Nice presentation. So the paper is now open for discussion. As I said earlier, if anyone is interested in making a question to Jaime, please just raise your hand using the application, or just send me a message through the chat stating your name and affiliation, and I will give you the floor to pose the question yourself. While we wait for the first questions, let me just remind everyone that CIBERNED Webinar Series are held every other week on Thursdays at 3:30 p.m. Although we will have a break for the summer in the next 2 months approximately, we will resume the webinars on September the 15th. And if you're interested in looking at the coming webinars, please just go to the CIBERNED website and check the program for the next few months. As I also said earlier, the webinar today is being recorded, and the recording will be placed in the CIBERNED website in the next few days. So if you're interested in reviewing the Jaime's presentation, or know someone who is interested in taking a look to it, please just feel free to address them to the website. All right, so any questions? I don't see any raised hands yet. No messages coming from through the chat. No questions? Okay, no messages coming through. I don't see any raised hands. Seems like you, Jaime, has been pretty clear in your exposure. So any questions, any comments? No? Okay, Ignacio,
since nobody's making any question, I just want to point out that these mice, the Firoc mouse, have a very wide phenotype. They show a number of deficits, not only in metabolic disturbances, but also in mood and in other types of behavior, and of course in neurodegenerative traits, as Jaime has been shown. That's only what I want to point out, that this is not only limited to metabolic disturbances. Okay.
Nice, thank you. Any other comment or question? Okay. I don't see any activity through the chat or any other raised hands. Okay, so this is the last call for anyone interested in making a question or a comment to Jaime. Okay, so if there are no questions or comments, let me just, before closing the session, to thank Jaime for a nice presentation and for his willingness to share with us his work. And thank you everyone for attending. I remind you that the webinar is being recorded and will be posted in the website if you're interested or know anyone who couldn't attend in person. And also remind everyone that we will have the summer break for the webinar series from now on, and the webinars will resume on September 15th, usually as all the year long on Thursdays at 3:30 p.m. All right, thank you everyone. Thank you very much, Jaime, and I wish all of you a very nice summer. Hopefully you will enjoy it and at least get a little bit of rest through the summer. And I'll see you in September. All right.
Okay.
Thank you very much, everyone. Thanks, Jaime.
Bye.
Bye-bye.